Good morning and welcome to the second day of uRos 2020. We will start with a keynote speech in a minute. Before that, just a few numbers from yesterday. We had about, on average, 100 attendees in the WebEx event, and on the live stream that was on YouTube, we had another 200 viewers in total on the stream, so not always on the same time. So that's quite good and probably more than would have attended at a non-virtual event. Yeah, with this, enjoy this second day, and I hand over to Mark van der Loo, who is chairing the keynote session.
Thank you, Alex. So it's my pleasure to introduce today's keynote speaker, Matthias Templ. Matthias is a fellow at the Digital Initiative of the Canton of Zurich in Switzerland. And he's a lecturer and researcher at the Zurich University of Applied Sciences. And he's also a lecturer and researcher by appointment at the Vienna University of Technology. Before that, he was working for, I think, about 12 years at the Statistics Office of Austria. And I would say that Matthias is really one of the pioneers of using R in official statistics. It's hard to mention official statistics and R and not think about Matthias. He was one of the first, maybe even the first, I think, to use R in any serious way in official statistics and starting contributing packages. And so he broke a lot of barriers for us, I think, not only in terms of technical challenges, like implementing algorithms that we can use, but also organizational barriers, like how to install an open source package in a regulated environment. So as a community, we can all be very grateful for that. Matthias wrote or contributed to at least 16 R packages that I could find, and in a very broad area of topics: disclosure control, imputation, packages for teaching, robust statistics, clustering. And lately, in the last couple of years, he has become very interested in functional data analysis. He's written in total or contributed to like 63 peer-reviewed papers, and recently he also published a book on functional data analysis with R. So a huge number of achievements from which we can all benefit, I think. Before I hand off to you, Matthias, just two more achievements. One achievement is that he's also the first person that I witnessed opening and drinking a beer during a talk at the Use R conference. But all in the name of science. All in the name of science. And I heard that he will become a father for the second time in December. So congratulations to you and your wife, Matthias, for that. One final remark for the people following this: please put all your questions in the Q&A. You can also do this during the talk if you're joining via WebEx. And then in the end, we're going to let Matthias answer them. So Matthias, I give the floor to you.
Thank you very much, Mark. Let me share my slides first. So first, thanks a lot to Alexander Koborik for organizing this conference. I think it's really runs smoothly and fine. Thanks, Mark, for the introduction. And also thanks to the Romanian team for initiating this conference series. Today, maybe I have scared some people because of my title of the presentation. It's an application of compositional data analysis in the area of functional data analysis. So today you will not see so much R code and R packages. You see more or less a primer on research in official statistics using R. So first, I had to introduce a little bit the topic of compositional data analysis. I think that's not well known in official statistics, still not well known, but we have many data sets which are compositional. And I will show today that if you apply classical statistical methods on compositional data, that's really dangerous, and you can receive very arbitrary results. So you should think about compositional data analysis. So the first part, so the first 20 minutes, I will introduce some concepts of compositional data. You will see some examples on compositional data and some comments on it. Of course, I can give you only a short impression about that. In the second part, also about 20 minutes, I will show you an application of compositional data analysis in the field of functional data analysis. And we will see what this is, and you will see some examples of functional data in official statistics. I think it could be quite interesting to see that. So thinking on Mark, a picture of Piet Mondrian, a Dutch painter. You see a composition. I think that's one of his greatest works. I think he needed about 15 years to finish this work, which he called The Harmony of Life, which lays under the beneath of the surface. And for him, it was very important to find the right proportions in the picture. So it's not about the size, the general size of the picture, it's about the proportions, the ratios between blue and the red area and so on. So that's typically compositional information, because if you would increase the blue area, automatically you have less space for the other areas. So automatically you have less space for the red area, let's say. So if we write these areas in some, let's say in some proportions, let's say the first area is about 1 divided by 15, so that's the largest in percentage. The sum of all that areas would be, for example, 100, if this data represented as percentages. So most of the area is in the red color, and then the rest. So the absolute values are not really important. Also for Piet Mondrian, it was important to find the right ratios between the areas and colors and so on. So if you see that the right picture, that's just a smaller version of the left one. It's not important how large the values are. It's only important the ratios are important. And that's compositional data analysis. In compositional data analysis, the ratios are important. So to describe this picture, you could either use all ratios, so the ratio from the first area to the red area, from the first area to the second white area, and so on. Or you could, like say, take a mean somehow, so a normalized area size, like this first area in the left upper corner, to a mean, let's say, of all ratios. And we will go further into details afterwards, but that's the main concept, to represent data as ratios. An old outdated view is always to say compositional data are only data which are closed by a fixed constant like 1 or 100. And we will see that's not true. We have much more compositional data which are not fixed as a constant sum like 1 or 100. An example here from Austria in interactive map, you see in each region you see how many percent of the people have a degree at university, have a degree at high school, and so on. So expressed in percentages. You see that, for example, Alex is sitting in Vienna somewhere here. We have more than, in some areas, more than 21% of the population who has at least the minimum requirements of school. So let's go a little bit more formal. So what is a simplex? That's a representation of compositional data. You see an observation here with D entries, so we call it composition. All these entries of this composition have larger value than 0. and this sum up to a certain fixed constant kappa. But this constant can be different for each observation in your data set. So that's somehow compositional data is always a representation of parts of a certain whole. Think of income parts that sum up to the general income. Think of wage components that sum up to the whole wage, tax components, and so on. The information on the whole is irrelevant, we will see, and yeah. So that's a multivariate data. So we are speaking always about multivariate data analysis here, where the relative information is important. So usually, for example, in geochemistry, we have a lot of compositional data expressed in parts per million, for example, or I already mentioned wage components, tax components, and so on. Expenditures of a household, for example, expressed in euro or dollars or something. Hours of a day. So if you sleep, let's say 12 hours, you have only 12 hours left without sleeping. If you sleep only 8 hours, you have more hours left for other activities. So it's also an inner relationship in such data sets. Let's see a very simple example. So there's data sets from the World Health Organization about alcohol consumption. So the mix of beer, wine, and spirits, that information sums up to 100. And we see just one observation here, Romania. That's a beer drinking nation, I would say, like Austria or Netherlands or Germany. So about 50% of the people drink mainly beer. If they drink alcohol, they drink beer, to 50%. And you see now this meaning of a simplex. You see not the observations only living in this gray area, and you cannot have an observation which are laying outside this area because there's a fixed constant of 100. So you cannot drink more than 100% of beer. What you see, that's, let's say, a shrinked space. That's not the Euclidean space. And that's the reason why you should not apply classical statistics to these data sets, because it doesn't make sense. Correlation does not make sense. It's always forced to be negative, just because of the data represented in the simplex and not in the Euclidean vector space. So compositional data follows another geometry, so-called eigengeometry. We usually like to represent the data in so-called log ratios. And we have some requirements which we'll define in some minutes. A data set can be compositional and non-compositional at the same time. That's just a little bit more modern view on compositional data. Thinking of a margarita. So the taste of the margarita is only based on the mixing of lime juice, triple sec, and tequilas. So depends only on the ratios between these elements. But so if you want to analyze the taste of a margarita, then the compositional information is important. If you are only interested to get drunk, then the absolute information on tequila is important. So a data set can be compositional and non-compositional, depending what you're doing afterwards. And there's a lot of examples of compositional data. Contingency tables are compositional data, probability tables, compositional tables, mortality data, basket data, hours of a day already mentioned. Every time where you represent your data in percentages or ratios of a whole, and so tax, wage, and expenditure data, poll data are typically compositional, and so on. And also in official statistics, we see a lot of data set with a fixed row sums, like 100%. And even probability density functions are compositions. We know that the probability density function, the integral is 1, and that's typically compositional. We will go afterwards to that topic. So if you click, for example, on the uRos2020 website, I only listed a few of compositional data there, the agricultural Lucas land coverage data, COVID-19 tourism, number of trips, intra-EU 28 trade data by member state, population counts as percentages, and so on. So there's an almost infinite list of compositional data there. There are some requirements. So if we multiply a composition by a constant, we should get the same results. So if we analyze the data, the original raw data and the composition multiplied by a constant, you should get the same results. Also, when you reorder the variables, you should get the same results. I think that's obvious. And the most important requirement is this subcompositional coherence. If you delete one variable in your data set, then the result should be not in contradiction to your previous results. So we will see an example there shortly. And if you don't select one variable, it should not have an influence of your results. But I can show you afterwards, if you apply classical statistics, if you suppress one variable and do the analysis on the rest, you will get different results as previously. Let's see a very toy data set example. We have expenditures of households here. So the first observation has 1,710 expenditures in euro on housing, and some on foodstuff, transport, and communication. That's typically compositional data, because if the household spend more on housing, he has automatically left less money available for other things, for transport, for example. So if you express the same data in Swiss francs or dollars or a mix of it, if we analyze both data sets, we should get the same results. That's compositional data, the aim of compositional data set. Even if we express the same information as percentages, so we divide 1,710 by the row sum, 3,800, we divide 950 by the row sum, and so on. So we get the expression in percentages, and still that's the same information as above, because the ratios are the same. So if we look at the ratios, 1,710 divided by 950 is equal 1,846 divided by 1,026, and it's equal by 45 divided by 25. And even if we don't measure communication, but only measure housing, foodstuff, and transport, and build again the ratios, we will see the numbers, the information in percentages changes, but the ratios still are the same. So 52.9 divided by 29.4, it's the same as 45 divided by 25. So again, a composition analysis where we look only on ratios, you will get the same results if you only analyze a subcomposition. Last example here, dataset from Eurostat, PhD students in some countries, and you see, for example, in Austria, we have about 4,978 PhD students studying technical science, 6,374 studying socio-economic or law studies, and so on. And what we are interested in is in the ratios. We want to see if, for example, in Austria there are more technical studies students in relation to all students in the country as in Hungary or something. So the absolute information is not very interested. You see here two variables of this data set, health against technical studies. And of course, you see that the US is highest because it's the largest country with the most students. So that's information is not very interested. That's the reason why people tend to represent the data in percentages. And you see the percentages of PhD students in health studies against the percentages of students in technical studies. And again, you can see, for example, Switzerland is here in the middle. Austria, we have not so much technical students, but also not so much health students. You see that the correlation is approximately 0. So what happens if we don't measure one variable? So if we don't measure the variables socioeconomics and law studies and build again percentages, we get the different pictures. It's the same data set, we just didn't measure one variable. And you see the correlation structure changes, the correlation is now negative, so that doesn't make sense. So you don't measure one variable and you get completely other results between the correlation of two variables. So in other words, classical statistics leads to arbitrary results, should be avoided. What's the success then? How we tackle this problem? We go from the simplex to the Euclidean vector space. So from this, there's many possibilities to do that, and it's well implemented in software, in R, and only in R. The simplest choice is using these centered log ratio coordinates. You present your data in these coordinates, and how to do that. So if you have one observation, one composition, each entry of this composition is divided by the geometric mean of the whole composition. And then we take the log. That we do for each entry. Here we divide by the geometric mean. As said before in the picture of Piet-Mondrian, we divide each area by a mean of the areas. And that's the same idea here. And we can show that if we do that transformation, we end up in an Euclidean space, and we can apply usual classic statistical methods. There's a whole book about this applied compositional data analysis. It's, I think, a very modern view on this topic with a lot of examples and a lot of applications. And there's software behind this book, the software called ROP Compositions, an R package. So all this theory you can apply in R. So let's switch to functional data. That's also interesting. A lot of data sets in official statistics are also functional. We see an example of Italy, income of persons in regions. So you see the whole income distribution of persons in each region here. And that's typically, you can express this as probability density function, and you can then compare these probability density functions for each region, for example. There's one region, for example, where you have higher income than in the others. And there's some regions where people tend to have less income. Or let's look at mortality data here, Austrian total death rates between 1982 and 2015. Unfortunately, there's no legend here, but you see that the log death rates against age. So age is somehow continuous information, and for each age, you can estimate the death rate. Or mortality by age and cause, population counts for each class, each municipality. We will see an application afterwards with such data sets. Children growths, Mark mentioned children's. It's quite exciting when an unborn baby has about 0.5 kilogram, and then he grows to 1 kilogram. That's quite an achievement. But when the child is already 16 years old and he has 70 kilos and he grows to 70.5 kilos, that you basically don't see. But the Euclidean distance is the same. And that's the reason why the Euclidean distance doesn't fit also to such data sets. So we need other concepts here. Let me formalize this once. Also, what are functional data sets? That's a samples that each data point lays on a random curve. And if you have an observation, x, and xi is the ith of observation at time t, on a continuous support in a certain interval. So this continuous notation is somewhat conceptual because, of course, we measure always discretely on time points t1 to tn, for example. So the first step is always in functional data analysis going from discrete data, fitting curves to discrete data so that we have curves. And the most popular application in functional data analysis is functional principal component analysis. And this is based on probability density functions. And probability density functions, in any case, a very important concept. So all our students learn that in every basic statistics lecture, they learn about the density function. And density functions are compositional. Let's have an application here. So we have population data in a certain region of Austria. There's 57 municipalities on 19 age groups times gender. So why I use these data sets? Because it's this data set is open data, so I can use it easily. And I was a motivated guy, is born there in Linz-Land, so that's myself. So I have some connections with the data sets. So let's look at the population pyramids, the population counts, so from the age here. And of course, the largest line here, polygon line here is Linz, because Linz is the capital and there's most of the inhabitants living in Linz, or quite a bunch of them. And there's a lot of small municipalities where not so much people live, and you see that on the population pyramid, you see that there's less old people, there's many people with the age around 25 to 50 and so on, and we can look at that for men and women. So this information is not so exciting, because if you, for example, if you print that information on a map, so for example, the total population counts, yeah, of course, Linz, most people, or many people living in Linz, that's of course then very black here, these areas in Linz, and you cannot see so much, so it's quite uninteresting information, I would say. Interesting, but we want to tell more story. Yeah. Of course, you can now visualize also the population means. You can visualize how many people are between 1 and 2 years old, and you can print that information, a map, and so on. But you will end up in hundreds of maps, and to compare hundreds of maps, that's not that what we want. We could also display other indicators, for example, the ratio of young people to old people represent such an indicator on a map, but it's only one indicator. We want to tell more on the data, so we want to visualize and summarize the output of the whole age pyramid in each municipality and want to compare them. So we are interested in the whole distribution age, so we are interested in the functional data. The first idea is to build ratios between the counts in any municipality. So we build just for each region, we look at how many people are between 1 and 2 years old, divided by the total number in the municipality. The next ratio is people are between 3 and 5 years old, divided by the total number of municipalities, of people in the municipality, and so on. So we just built relative information, because we see these absolute values are not so interesting because it's dominated by Linz, for example. And there could be some questions like, will the region of Linz have a larger, relatively higher amount of young people than, for example, in other areas? And these questions we would like to answer. So if we present the proportions of these 57 population counts in each municipality, you see that curve. So again, there's less people which are old. Many people are around 50. So the proportion of people who are around 50 is largest, and so on. And where you see the tendency that the women get a little bit older than the men, and so on. So these are almost density functions, but again, discrete measurements, so we have to come from discreteness to continuous functions first. So the goal is to analyze this density of the age distribution after a dimension reduction, like using principal component analysis. We know that density integrates to 1, and density consists of only relative information. So the standard methods of functional data analysis are really not appropriate, I would say, because if you, for example, sum two densities, so a convolution of two densities, the result is not the density. If you multiply a density with another density, the result is not a density. I will show a picture in a minute about that. Even we will see that with the classical approach, you can even, for the fit, if you want to reconstruct the data with the first two principal components, for example, you can have negative estimates of density values, also something what we don't like to have. And already mentioned with the age of the child, so the Euclidean distance doesn't make sense much. So what is the solution? So in general, a probability density function is a compositional vector with infinite many parts. So we use the concept of compositional data analysis and these log ratio approaches, and we call that somehow the data lays in a so-called base Hilbert space instead of the Lebesgue standard measure. So the all integrable function, usually the Lebesgue space is that space where the data lives, and we don't want to analyze this data set. So our data sets, we define a so-called base Hilbert space. In this base Hilbert space, we can define a norm, an inner product, addition, multiplication. That's quite complicated. I only want to see want to show you the results about addition and multiplication later. And the good news is that if we multiply two densities, or if we add sum up two densities, the result is again a density then. And also the good news is that we can transform our data sets using a log ratio transformation to the base space. And in the base space, we can apply the usual methods, classical statistical methods. So that's already the addition and multiplication. For example, if we add two densities, the result is again a density in the compositional approach. In the classical statistical approach, classical functional data analysis, the result is not the density. Also, if we multiply a density by a constant, the result is again a density in our approach. In classical statistics, it's not. So coming back, the first thing that they said, smoothing is necessary. How to smooth data sets? There's many possibilities, and often we use natural cubic splines between, so we define knots, and between each knots we fit a spline with some constraints that for smoothness. So we can do that, for example, with our data sets. We see the age distribution in municipality 40101, and so that's our actual values, and we can fit the spline here, for example. We can do that also for men and women here in the original data set, or in the CLRs and the centered log ratio transformed data set, where each ratio is divided by the total, and also by geometric mean and taken the log. We will come back afterwards why this is so important, and we can do that for all municipalities. So each line represents the age distribution of one municipality. So how to do that? We already said we want to do principal component analysis. That's the most prominent application of functional data analysis. So we compare this high dimensional data and fit represent our data sets with less scores. So that's typically done with principal component analysis. I don't want to go into detail in the formulas here, only the idea. So we want to describe the main variability of the data set with k-linear combinations of the original variables. And we took these combinations like that, so that in the first principal component, we explain the most variability of the data set. And the second direction, the second principal component is then orthogonal to the first principal component and explaining again the most of the rest of the variability of the data and so on. So the output are so-called eigenfunctions of a covariance matrix describing the variables and scores, representing the observations. And typically we use the first two, let's say two principal components to describe, to interpret our multiple data set, and we do that through a biplot usually. So don't be afraid. So that's quite a standard approach of principal component analysis. And for our new method, that's quite complicated. So there are quite complicated equations. So I also do not want to go into detail here, but the main idea is to represent the data first in centered log ratio coordinates and then do a principal component analysis. So the idea is quite simple. It's efficiently implemented, and so let's go to some practical examples here. First is a simulation. We simulated 100 densities from a gamma distribution. We took just different values for the parameters for the gamma distribution. That's our data set. Again, a high dimensional data set here, and we have 100 of these curves. So what we do now is to apply the classical approach, functional principal component analysis, and we will see with the first principal component, we explain about 60% of the variance in the data, with the second about 30% of the variance in the data. Keeping that in mind, so on this lower harmonics curves, we go into detail in some minutes. What is the difference when we use our approach? So if we first present the data in centered log ratio coordinates and then apply these functional principal components, we see that the explained variance with the first component is almost 100% already. So it's much better we explain much more variation in the data with the first principal component. And with this first two principal component, we explain basically the whole data set. Also, the scores doesn't look like nonlinear anymore, they're linear. So in general, we have much a better fit. Yeah. And if you use now these first two principal components to reconstruct our original densities, we will see with the classical statistical approach, we also receive negative densities and changed a lot, I would say. And what if we use the first two principal components with our new approach, we can perfectly reconstruct our original densities. So having that in mind, that we really get better results, we go to the practical application now. So let's discuss these results on this Austrian population data here. So what if you apply that on these age distributions? We see that with the first principal component, we explain about 80% of the variance in the data. And with the first two, we explain already about 90% of the variation in the data. We see the first principal component. We have higher scores for the elderly people. And for the second principal component, the scores are very low for the people between about 69 to 90 years old, and for the small children. And in the middle age range, we have positive scores. let's take a biplot of that. So the first principal component against the second principal component. And we just represent the abbreviation of the names of the municipalities, of the counties. And for example, Gmunden, GM is quite on the right, has a high score on the first principal component. Also Gmunden here has also a high score on the first principal component, but also on the second principal component. So, and with this information, together with a map, we can now interpret our results. Let's look at the map here, the so-called LISA maps. So if you have high scores, that's for women's, if you have high scores in the regions and also around the regions, we get the red. If we get the blue, if you have low scores and all other regions around the region is also low. That's called LISA maps. Then we get the blue here. What we see, the red area in the bottom, that's Gmunden and Enstal. We see the people are quite old, relative to the whole age distribution in these regions. What we also see that young people are moving to the capital, Linz and surroundings. And above Linz, we see we can interpret there's a lot of families here. Why I can interpret that, if we go back to the scores here, we see, for example, Gmunden has very large score on the first principal component. And if we look at the harmonics here, we see a large value of the first principal component means old. There are relatively more old people than young people. Okay, so I can interpret that maps also the second principal component. For example, here in blue, we have Rohrbach, Scherding, and surrounding. We see that way too much old people relative to the whole age distribution live there. Especially for the women's. So the women's emigrated there. The women's gone to Linz or somewhere else to study somewhere else or something. Why we can interpret that? Because if we look at the scores again for the women, and we look, for instance, Scherding has a high score there on the first principal component, but also on the second, a negative one, and a high negative score on the second principal component means there's too much people between 69 and 92 years old. So with combination of all these graphics, we can well interpret these graphics. Also, for example, on the highway here, that's the red zone here. We have high scores on the second principal component. What means high score on the second principal component? We can look again here. Perg, for example, Linzland, the area where I was born, has high score on the second principal component. What means a high score on the second principal component? That the people between 30 and 60 are overrepresented. There are more people, relatively more people to the whole age distribution in that areas. And that we see here, so we have a lot of people who are fit to work in that region here. So to summing up, what was the main idea for this presentation? It was not so much focused on R. Even I would have one slide for software afterwards. So it should. So compositional data analysis is not well known in official statistics. Unfortunately, there's a lot of data sets which are compositional. And for example, looking at contingency tables, probability tables, where we always built in compositional in official statistics, but also if we look at wage components and so on, expenditures, this all are compositional data sets. And knowing now that we have a lot of compositional data, please use this theory of compositional data sets, because if you apply classical statistics, you really can end up in very arbitrary results. I also wanted to show some give a primer on the need and usefulness of new research, especially in official statistics, especially when people working in the statistical offices, it's always a fight to have the freedom to do some research. We all know that. We have so many projects which are not research-based, I would say. We have so much other things to do. It's really important, again, to have a little bit focus on research in official statistics, also from the statistical agencies. We shown that with the compositional approach, we improved functional data analysis, so the results are really much better, I would say. But this is also not known in the functional data analysis community. That's a very new approach. With this application, I think it was only one special application, but you can think about income distributions in regions, for example, and so on. And you can apply this same approach on such a data set. Even it's extended, the approach is also extended for regression. So regression for functional data, if you have a response which is functional. There's another ideas and applications, for example, in small area estimations, when you have proportions. There's also papers about, for example, fitting confidence intervals of ratios for complex surveys. And so there is some activities in that area. We applied it also on mortality statistics with very nice results, but unpublished yet. And as said before, it's also extended to functional regression context. And there's a new paper, which have more mathematical foundations of these probability density functions in base spaces by some Czech authors here. So coming back to R as the last comment, so all these methods for compositional data analysis are implemented in the package compositions and also in the package ROB compositions. ROB, because we're always interested in robust estimation. So there's always, for example, if you do discriminant analysis, there's also a robust version there. Compositional spline, if you want to do the spline fit for compositional data. And there's a lot of methods, for example, for imputation of missing values, principal component analysis, for contingency tables and related tests, there's functions. For these log ratio transformations, there's a function called sen-lr, which we use today, or more general isometric log ratio transformations. For cluster analysis, for discriminant analysis, and many, many multivariate methods, there are the compositional versions implemented in this package of compositions. And we have also about 45 compositional data sets included, so that you have an idea which data sets could be compositional. Yeah. Thank you very much for your attention, and I'm looking forward to some questions. Thank you.
Thank you, Matthias, for really an eye-opening talk, I think. If I speak from my own experience, I think that we sort of struggle with these compositional problems every day when we are working with, for example, structural business survey data, where you also have all these linear constraints, but also in our output. And I think one of the things is to name the problem correctly. That's exactly what you've been doing. Well, one of the things that you've been doing is to point out that there is a existing theory and technology to actually handle this. So very interesting to me. I'll have a look in the Q&A, and if people want to ask questions to Matthias, we have a few minutes, so please don't hesitate and put questions in the Q&A. I do see somebody who said, Beate Siek, who said, great talk, thank you. So that's one you can take home or keep home already. I have a technical question while we are waiting for other questions to come in. So the compositional data you have talked about, there is all the data is positive, and there is like one sort of linear restriction. And in some of the data we work with, we have multiple linear restrictions. For example, if data is in a table, maybe you have two marginal structural business survey. There's a sort of system of balances, and I wonder if it's possible to extend to those cases if you can adapt or generalize the transformations that you use.
So if you're interested on the relative information, so one component is one component dominant to another or something, or if the ratios itself are interested, then you can, for each of these subcomposition, you can apply a log ratio transformation. You will, so independently, so for each of your parts, which summing up to a whole, you apply independently a log ratio transformation. The only thing is also that very difficult, to applying such a transformation is very easy to apply afterwards some statistical methods. That's very easy, but the interpretation is always a little difficult, because remember, you divide each part by something, a geometric mean of all other parts, for example, and take the log. So in the log ratio transformed variables, you have your values of your observation there, but divided by the rest of the others. So also the information on the rest is somewhere in that ratio. And for an interpretation, you always have to think about that. That's not the original data what you analyze. That's ratios. And for some application, that could be then quite tricky.
Yeah.
And typically, we try to use some other balances. Like not this. We don't like to apply this centered log ratio transformation, but using some isometric log ratio transformation. That would now go into too much detail, but to ask yourself use case and data specific thinking. What makes sense in your data set? Can I interpret that ratio well? So why not take the ratio of the first variable divided by the second and the third? And the other ratio could be the second variable divided by the first variable. So taking individual ratios for for reasons of interpretation.
Okay, thanks. I see there's some questions coming in, so let me have a look quick. I hope I pronounced your name right. René Logger says you have divided your population in different regions into age groups. There is one or two regions. There was a pop-up, I'm sorry. There is one or two regions out of many that has an age group which is 0. For example, there are no children below 1 year in a certain region. What can you do in such a case?
Luckily, in this data set, we didn't have zeros, but zeros are a major concern in compositional data analysis, because with a zero, you cannot beat the ratio. So you have to do something. One idea is so for such count data, you add a small constant, not too small constant, but yeah, you say you didn't observe a child which is 1 year in one region, but it could be there. So with this philosophy, because with zeros you cannot work. So either let this specific region out of the analysis, or you have to cheat a little bit with imputing a 1 or something.
Beate Siek says it's very strange that almost nobody is using these methods. I think I agree. Do you think it's because people are not aware of these methods, or can you imagine other reasons?
Yeah, people are not aware. I can tell you a story how I detected this topic. So we wrote an article about cluster analysis 20 years ago, or 15 years ago, and we want to publish this in some geochemical journal. And one reviewer was from the community of compositional data sets. This is a very small community in Spain, and she said, what we're doing is wrong. We have compositional data. Why we apply classical statistical methods there, cluster analysis? And we said, what? Compositional data, are they crazy? And then we done a revision, and yeah, we was not quite well in that area as second revision because she insisted. And then yeah, we started to think about this problem, and we needed about 2 years to understand these concepts. So it's first that the concepts are not so easy to understand. Then there is limitations always, as René said before. Zeros always is a pain in the ass if you have zeros in the data, in compositional data. Yeah, and all these two restrictions so complicate the theory, but the theory is really well defined, I would say. And zeros in the data makes it not so applicable sometimes.
I think that having things like the software available so people can experiment with it will also help a lot. So that's also a great contribution. Even if you're not fully aware of the theory, it already can give you a feeling of what's happening when you can experiment with the results. So that's I think that paves the way in for people.
And of course, there's only the R software which having methods of compositional data sets included. There's no other implementations, I think.
Somebody sent a question also in the chat, so let me have a look. Quickly. From Irvind. Hi, Irvind. He says, very interesting talk. And one question is, why is it important to smooth the data before PCA? Wouldn't the result of PCA anyway be smooth curves?
No, also the concept, also we define our data set to be functional. So basically, for each age, age could be continuous, we can find the proportion of people having exactly this age. So if you want to define so then the second thing is to compare different functions. Also, I think it makes sense to smooth before, because as we saw in the first picture of these ratios, the polygon lines was quite unsmooth, and I think it's just from the general concepts of smoothness of age should be somehow smooth for the population. It makes sense to smooth it first. Smoothing is in general a good idea. So think of that you have different data sets from Austria. In Austria, they represent the data like in 19 age groups, and in Netherlands, they represent the data in 25 age groups, and different one. So what you do, smoothing is the only possible way to make them comparable. Also for different, if you measure some other data sets where you have measures in time, if you have different timestamps, I would say, for two different data sets, you cannot compare it. You can only compare it if you first smooth the data and then compare.
Okay, thanks. I think we are out of time. I see there are some other questions coming in the chat and Q&A still. So maybe Matthias, you could have a look and see if you can answer some of them in the chat still. Thank you very much again for a very interesting and wonderful talk. Even though the topic was complicated, I think it was quite accessible. And with this, I think I'll hand over to Alex, and we will move to the next session. Thank you.
Thank you, Mark, and also thank you, Matthias, for the nice presentation. Yeah, my job right now is basically only to hand over to Nicoletta, who is actually chairing the next session, and I will also assign the next presenter role. Nicoletta, please start your session.
Thank you, Alexander. Before start the next session, I would like to thanks to Matthias for the great presentation to us. Thank you, Matthias. And now we have the third session, scientific session, named Dissemination and Visualization. Every participant has 15 minutes to talk, and 3 or 2 or 5 minutes to have discussion at the end. The first presentation is taken by Sebastian Ruiz Santa Cruz, researching at Shanghai University, revisiting Rogers and Castro's multi-exponential model, migration schedule. So, Sebastian?
Yes, can you hear me?
Yes, you have the floor.
Thank you very much. I will share my screen. Okay. So good morning, everybody. I'm Sebastian Ruiz Santa Cruz. I'm in this moment an adjunct researcher at the Asian Demographic Research Institute at Shanghai University, and it's a partner of. I'm also partner of the External University in Colombia. I'm doing this branch of the work with Madeline Villarreal Fuentes, which is working at the International Labour Organization, and she's advising me to give more content to my results given from the PhD thesis I made 1 year ago. So let's start saying why the migration age schedule is important. And it's important because it describes the migration age pattern associated with selectivity as an interaction of push and pull factors in origin and destination areas. So it is also allows visual comparisons about the intensity and the migrant population general structure. So for demographers are describe the structures of population, it's the most important thing, and also for describing the migrant structure as a component of the labor market is also important. So the model it estimates a migration schedule based on exponential curves that belongs to a demographic behavior. We will see later in a slide we have how it is composed. And give us some demo economic parameters. And those demo economic, I called, relates to labor force participation. So it is important to describe these parameters in the model. Other alternatives are kernel smoothing that the institutes used to implement sometimes to model the migration schedule, and also to estimate sometime curves before under 5 years old. So, and this model can also be used for that. Other definitions in the model have been taken recently by Tom Wilson in Australia to describe the post-retirement curve. Following some theories that there is people migrating at the end of the life. And Other options as well are non-parametric measures of this curve based on some parameters, I mean created by the form of the curve instead of being like mathematical parameters. So the uses has been taken by many years in some countries that still methods to smooth and grasp the mean behavior of the migration calendar. And there are opportunities also to estimate, as I said, children under the 5 years old. However, we have to be careful because we need to see some kind of historical data and taken carefully because sometimes the under 5 are overestimated with the model. So we have to be careful with the empirical data. And also population projections needs sometimes smoothing and also project those parameters to see how labor force is incorporated. So it is used to theoretically for that in some papers they are trying and contradicting as well. So we will see why are revisiting this model. So the general model or the more complete model is a 13 model parameters. However, it has 4 models. We have 4 models. One with 7, 9, 11, and 13 parameters. And most of the curves describe migration. If you can see my pointer, we can see that this is, for example, the curve that describes the infant migration, and the other curve describe the labor force migration, and then this will describe the retirement peak migration, and so on. If we have more parameters, we will see that it is going upwards or downwards, and we will describe it with another exponential. So in the original paper, they called until those parameters and until 13. However, with the initial value problem we have here, because this is made by an optimization, we will have to choose one initial value. So we said, why this value? And it just started in the paper, and in the paper just said, these are the initial values. And I said, okay, well, but what happened if we change it? All those initial values for this optimization, and then calculate those parameters, and then other parameters which are the ratios, which seems to me more stable and more accurate to give like a discourse to the labor force and in the labor International Labor Organization can use it in some way. So how we did it? First of all, we did a rate calculation for the migration rate, right? So we have the immigrants, and then we have the population in the denominator from 5 years ago. By age and sex, we can have it. This is not taking into account mortality. It's just to have this exercise. And then we have kernel smooth on those rates to help the model to fit. However, we can do it without it. But in this case, I did it to help the model, because in this case, we will see we have a lot of variance. So I did it just for that reason. And then we will just take the mean square error and the mean absolute percentile error and see which is the minimum. We simulate one value at a time for each parameter, saying that this is Bayesian thinking. It's not a Bayesian method. A Bayesian method is not, it's not Bayesian, but it's a Bayesian thinking. Like we don't know, so we have a prior, like uniform prior. We don't know anything about the parameter. So we developed with another colleague, previously to this this ongoing project, we developed a package in R. Is already on GitHub, so you can download it and place your issues as well. And it's based on an S3 class. So we use a method and oriented programming. So we use a method, and then we establish this method, which is a linear regression. We take the logarithm of the curve, and then we perform linear regression. But then you can you play with these functions, and then this is like the whole example. They're taking 200 iterations on, and this is for Spanish migration, the Asian-specific migration rate, and then you can see the class here in the R model, and then you can take the parameters out like usually you do in R. This is the function best middle mode which adjust this, like doing almost a loop, just taking calculating the gradient if the function doesn't have it, so this discard it. Okay, you can just go into the website and see how we develop, and then I plot it now, which is here in the plot, and then you can see which is the best mapping, or MAPA in Spanish, and in under R square. So you can because those measures are given by the USSP, the International Union for the Scientific Study of the Population, and in the website they say you can take both to check which is better. And okay, in this case, let's say it's the 13. However, it's 200 simulations. We can do it with 100,000, as I did it for the exercise. So the application results, I will just show a little bit of the package. You can see it here. And it's the same thing I'm showing you. And this is the exercise I did when I was doing my PhD. I did this shiny, and you can see this from the Argentina to Bolivia. So you just change it here, and yeah, take Colombia, and yeah, you can just take it. You will see standardized migration rates and so on. And then we just realized that everything ended with this method, and everything ended up in 11 or 13 parameters, more or less 115 curves out of 139. And many curves doesn't fit because at the beginning of the curve or so many curves there was another peak. So that I'm like proving now, testing if there is a child migration delay. So we are testing, we will see in the other things. It can be a mechanism of migration, like pioneerism, and we will see that it's a worse estimation of the retirement peak because the exponential curves are like eating the function with this method. So we'll have this example for Argentina to Bolivia and Colombia to Venezuela for men and women. And the first thing we can check here is that, sorry, I will go back. In this case, always, but under the theoretical model, this is less than this, and here the results are showing with that we can like switch sometimes, and yeah, there's like weird results on those for women and male, and it is not always less the mean peak. So then we check with the initial values and the mean square error at the end, and we check that those parameters are not really significant. And this is for many models, and in many models, they are not significant into the optimization. So we are like kind of re-evaluating the model, like theoretical model. This is not the mean peak of migration. This is just a parameter in our optimization. So we can see like defining parameters, the distributions, and this is helping us to construct priors, like beta priors for next steps, like in a model. We'll see. So those are the levels, A2, A4, then all the parameters for those ones, and the location parameters. I told that they are following something like normal or something like this. And then with all those parameters, I've constructed a typology for Latin America, and we can see that Latin America has four regions, let's say, for kind of countries that migrate, with one with more labor and postponed retirement, one with more infant dependency and more asymmetric curve, one with labor curve and extended among ages, and one with the asymmetry and age migration. And,
Sebastian?
Yeah, tell me.
Please, 2 minutes more.
Okay.
And maybe conclude. Thank you.
Yeah, I will conclude. So we can say, like as a whole, we can say that the more child dependency in this system, the less is the symmetry of the curve. So this implies that maybe it's more labor migration, more aged labor migration that are bringing more children. Sorry. Why is important to ILO is because to establish historical measures to project could be part of a country classification, and the best part is we can know now something from the statistical registers, and can we replace, is the question, something from the statistical registers from labor surveys in countries. And the ongoing work, as I told, this is with the Statistics Colombia and some with the Treasury Colombia as well, with the administrative registers, the hierarchical model to incorporate beta priors and some inputs, and combining with the information from ILO stats, the bulk of we have. And thank you very much.
Thank you a lot, Sebastian. Of course, the migration is very challenging issue every time. If there are questions in the Q&A section or not, if people would like to write something to Sebastian, please use the Q&A question. Thank you again.
Okay, thank you,
Sebastian. We move now to the second presentation to a close friend of the uRos conference, Øyvind Langsrud from Statistics Norway, with a presentation of sparse matrix tool in R for multidimensional hierarchical aggregation. So, Øyvind, please, you have the floor now.
Yes, then I try to share. Do you see it? Do you hear me?
Yes, yes.
Yes.
We can see it and hear you.
Yes, I'm Øyvind Langsrud from Statistics Norway. And I'm a senior researcher at the Division for Methods. And today I will talk about functionality for multidimensional hierarchical aggregation. And this is implemented in R, the package SSP tools available on CRAN. And the main function is hierarchy compute. And I will start by looking at the web page from Statistics Norway, and I want to find data about municipal accounts in the so-called stat bank. And To specify a table, I had done some selections, contents, year 2019, some regions, 2 accounting scopes, a function within primary and secondary school, and type sick pay reimbursement. And the result is a table with some accounting figures. And if we look at the underlying data, we can say that we have 6 dimensions. 1 year, since we look at 1 year at a time, 462 municipalities, 2 accounting categories, 2 accounting scopes, 208 function codes defined by a hierarchy, 208 type codes defined by a hierarchy, and the challenge is to compute for all the 84 million combinations, compute values for all the 84 million combinations, even if 90% of them are 0. And from an input file with about 800,000 combinations. And in input function and type codes are from the lowest hierarchy level. And the missing combinations in input is treated as 0. And to do the computations, hierarchy specifications for function and type are needed. And this was, in fact, an actual challenge because within a modernization project, the plan was to do the computations using an implementation of the validation and the transformation language. And this turned out to be too inefficient. And I was asked to try to solve the problem using R. So I call this the 80 million challenge. And a problem is that these hierarchies are messy. And to describe the methodology, I will first look at a simple hierarchy, which can be described by 3 formulas. Europe is EU plus non-EU. EU is Portugal plus Spain, and non-EU is Iceland. And the information in the formulas can also be written in the table like this. And the column with levels means that you need to compute EU and non-EU first, and then Europe. And the hierarchy can also be described using the standards in STC table or PAL Argus. But the formula specification on the right side are more general. A tree structure is not needed. The sign can be negative, and these can be called free hierarchies. A simple example is to specify Europe and EU and non-EU in another way, like this. Europe is the sum of Iceland, Portugal, and Spain. So the direction of the arrow is important. And in addition, the color is important. This is used to specify a negative sign. EU is Europe minus non-EU. And the first part of the computation process is to make a dummy hierarchy matrix from the hierarchy specification. Input codes are columns, and these are found in the maps from in the row where the level is 1. And to create a dummy hierarchy matrix, the algorithm contains matrix multiplication for each level. And the levels can be found automatically. And here, both these specifications give the same dummy hierarchy matrix. Input codes can also be included as rows, and then a parameter input in output is true. But I will use false here. So this is the geographic hierarchy. And in the first example, I will also consider a very simple age hierarchy. Now, input in output is true, so the codes young and old are both in input and output. This information is input to the function hierarchy compute. And in addition, we have an input dataset. And so this is how it looks in practice. The input data, the function call, and the output data. And output is computed from input by a matrix multiplication. So a model matrix is involved, or the transpose of a model matrix. And now about how this model matrix is created. The final model matrix is the result of crossing a separate model matrix for each hierarchy. And each is a dummy hierarchy matrix extended to match the data. So at the bottom here, we have the young column replicated 3 times. And crossing is done by the column-wise Kronecker product. And now an extended example where year is an extra dimension without the hierarchy. It's just a factor specified by row factor. And here there are 2 hierarchies and 1 factor, but in general, there are no limits to the number of hierarchies and factors. So this is the computations behind the scenes. And by using dots instead of zeros, it's easier to look at the matrix. And since the sparse matrices are used, the zeros are not stored in memory. Now on stage again, and back to the extended example. Now we change the specification from for year from row factor to call factor. Output is the same, but column order can differ. And now computations behind the scenes, now they are different. And reorganizing to wider formats can improve efficiency. And by specifying the output parameter, it's possible to see the matrices. Holes may occur because of incomplete inputs, and these are filled with zeros. And to solve the 80 million challenge, region was specified as call factor. And now we take a look at these messy hierarchies. The function hierarchy, it's not a simple tree structure, and we also have a few red arrows, which means negative signs. And the type hierarchy, so here we have a lot of red arrows. And the 80 million challenge was solved in 20 seconds on my old laptop, and half of the time was used to reorganize the results. And I will just mention some extensions and spin-offs after mission completed. It's possible to compute only some selected combinations. Duplicates can be handled in different ways. Two-way computation is possible. The model matrix can be the primary output, like this, and combination with a formula is also possible. Hierarchies can be specified in several ways. And it's possible to use model matrices within statistical control tools. And this is the case for the package small count round. And here are some snapshots from the vignette. Hierarchies are inputs, and model matrices are computed in the background. And finally, the conclusion. I have talked about sparse matrix tools in the R package SSP tools. I use sparse matrices according to the matrix package, and then you don't waste memory to store all the zeros. The function is hierarchy compute, and there are other functions according to the previous slide. Thank you.
Thank you, Faiven. Very interesting presentation. There are no questions yet in the Q&A section, but I have one for you. It is very technical presentation, and I would like to know more about the application in statistical offices. Could you please give us more details about or examples for statistical institutes? Thank you.
This was developed because of very specific computations within a specific area in Statistics Norway. So that was the reason why it was made. And this was very important for Statistics Norway. It is within this account computations. So, but afterwards, I realized that this functionality was also could also be used for other things, especially the creation of these matrices from hierarchies that can be used within the statistical disclosure tools. But you can also imagine other areas. But what I have been involved in so far is this starting point with this accounting computations.
Thank you. We have a question here. This is a really nice tool. Are there any plans to read standard hierarchical classification like those in SDMX registers?
Can you repeat?
Are there any plans to read standard hierarchical classification like to those in SDMX registers? I'm not know the details about those registers, but once you read some classifications, you can always transform them into this other formats, and so it's the question of transforming this classification into hierarchy specifications that can be used. So I think it's very possible to use it in many ways. Thank you. If there are no more questions, thank you again, Faiven, for your presentation. We move forward on the next presenter. We talked to Julian Kremers from University of Copenhagen, Denmark, with presentation analysis of trajectories into retirement using the Danish labor market register. So, Julian?
Yes.
You have the floor.
Share my screen. Can you all see the presentation?
Yes, we can see it and we can hear it.
Great. Yeah, right. So what I'm going to present is research using actually two methods to analyze trajectories into retirements for the Danish labor market registry. So the Danish labor market registry is one of the few longitudinal registries that Denmark Statistics maintains, and it contains labor market statuses of all individuals living in Denmark on a monthly basis. So what you see in the slide is an example, so a simulated example of how this registry looks like. And you see that for each month, we have one or multiple labor market statuses for individuals, and also noting the amount of hours that this individual was in this status in each month, as well as the start and end date. Now, we're not going to use the entire labor market registry, but as I've already said, we decided to focus on trajectories into retirement. And that was inspired by the fact that in Denmark, a policy reform in the so-called early retirement pension was made in 2006. And this policy reform basically meant that the eligibility age for receiving such a pension was increased slowly. So everyone with a date of birth before 1954 could make use of this early retirement pension from age 60 onwards. But individuals born at a later age, you can see later year, this age was slowly increased until it's finally related in relation to life expectancy. So as I've said, we've decided to investigate two methods to try to look at this data and see what use these methods could be. And the first method that we decided to look at is so-called sequence analysis. Now, in sequence analysis, what is done is that we have sequences of observed states for a set of individuals. So in our case, we decided to look at individuals from age 58, so the month they turn 58, until the month they turn 63. And we decided to look at individuals born in 1950 and born in 1954. And for those individuals, we look at their labor market state, which could be one of five. So either they're full-time employed, part-time employed, outside the labor market, which basically means unemployed. They could have received pension, or they could be deceased. And we thus have 60 of those labor market statuses because we follow each individual for 60 months. And you can then make a kind of plot as you see in the slide. So here we see an example of the labor market states of 10 individuals from the 1950 cohort. And we call these observations, we call those sequences. So as you can see, for example, individual number 2 and individual number 5 here were receiving pension already for the entire period. So this could, for example, be disability pension because the individuals were already receiving that before age 60. But on the other hand, individuals 10 and individual 3 were full-time employed for most of the observation period. Now, the idea of sequence analysis is that we sort of try to compare all of these sequences. So we compute different scores that indicate how much the sequences differ from each other. And then we try to cluster these differences so that we get a set of typical, in this case, labor market trajectories for this specific cohort. So if we do that, if we compute differences between all pairs of sequences in our data set and subsequently run a cluster analysis, using R. So there are several packages that you can use, but we use the TrawMiner package, which is especially useful if you have a social type of data and not, for example, DNA sequences. And if you do that, then this is the type of output that you can get. So here we specified in the cluster analysis that we wanted it to output 6 clusters, and in this case, 6 typical labor market trajectories for the 1950 cohort. And the labels that we gave all of these clusters, those are the ones that we made up ourselves. So, for example, the largest cluster here contains 20,000 individuals that were born in 1950, and that's the cluster on the bottom right. And we said gave this the name full-time late pension because, as you can see, most of the individuals in this cluster were full-time employed for the entire observation period, and at around age 62 here, a small part of them decided or started receiving some kind of pension payments. And then with relation to this early retirement pension, you can see these two clusters on the top and in the middle right, which contains individuals that at age 60 most likely decided to make use of this early retirement pension, because you see a sharp increase in the proportion of individuals that are receiving that pension for both these clusters. Now we can do the same thing for all individuals born in 1954. So remember, for those individuals, there was a change in the eligibility age for early retirement pension. And you really clearly see that also in these typologies. So the way the typologies look doesn't really change that much, but for these two early pension categories, you clearly see that there is no sharp decrease at age 60 anymore in the amount of individuals receiving pension, but that decrease starts at a later time point, so at age 60.5 and at age 61. So you can see back in these kinds of typologies the effect of the policy reform in early retirement pension age. But one thing that you can't do with this kind of analysis is if we want to model the time to pension. So we show that there are differences in when people start receiving pension funds, but we can't model an individual effect on when you retire. So in order to do that, we looked at another type of model, which is called joint models for longitudinal and survival data. So why did we decide to look at that? And what is it? So basically, this type of joint model means that we're combining two outcomes, one longitudinal outcome and one time to event outcome. And in our case, the time to event outcome is the time to retirement. So we're interested in modeling the retirement hazard, and we model that jointly with the longitudinal outcome, which in our case is a labor market state. So that's either being full-time employed, being part-time employed, or being outside the labor market. So for simplicity, we left out the death state, because in that case, we would have two time to event outcomes. So the longitudinal outcome is modeled using a hierarchical multinomial model. You can see here to model the probability of having a certain labor market status. We do that using a set of covariates X, which can either be time-varying or fixed. And we have a random intercept. So each individual has their own probability of being full-time, part-time employed, or outside the labor market. And we do the same thing in the time to event model. So we have a proportional hazard type model with a set of covariates again, and this UI, which is a random frailty, so basically a random effect, and each individual has their own retirement hazard. So we have two submodels, and these submodels have to be linked in a certain way, because we might be interested in the link between the retirement hazard and the probability of having a certain labor market status. And then in our case, we decided to model that using a joint multivariate normal distribution for the random intercepts and the frailties. So we are basically modeling a covariance or a correlation between the random intercepts of, for example, being full-time employed and the frailty, so the retirement hazard. So why this and why not more simple survival kind of model, for example, a Cox proportional hazards model? And that's basically because the retirement hazard and the labor market status are endogenous variables. And if we would use a Cox proportional hazards model, a simple survival model, we would have bias because of that. Two other reasons which are not necessarily present in our data set are if you might have non-random dropout in a longitudinal outcome or measurement error. Then such a joint model can also correct from bias caused by these issues. So in R, we implemented this model as a Bayesian type model, and that's a really nice package with which you can do that, which is also very flexible in terms of specifying your own models, is the R-stand package. So that's the way in which we implemented this. And then the results, as you have seen, the joint model consists actually of two submodels and then this link. So we have a submodel for the longitudinal part, the labor market status, a submodel for the retirement hazard, and we have this joint variance covariance matrix. So our results also come in three parts. So first of all, we can look at fixed effects of covariates for the survival submodel. So in our case, we included two covariates, sex and education level. They're both categorical covariates. And we can then get hazard ratios together with credible intervals, because it's a Bayesian analysis for both of the cohorts. So note that we did two separate analyses for both cohorts, but of course, a better analysis would be to include them in the same model. And here we see that, maybe not unexpectedly for these cohorts, is that the hazard ratio of sex is larger than 1, in this case meaning that the retirement hazard for females is larger than that of males. So basically females tend to retire earlier. And the hazard ratio for education is, at least in the 1954 cohort, lower than 1, meaning that a higher education level leads to a lower retirement hazard. Then the longitudinal submodel, so that was a multinomial hierarchical model, which means that we can get odds ratios back from our analysis. And note that the credible intervals here are for the coefficient and not for the odds ratio. And we then have two parts in the output, one for the odds of full-time employment versus being outside the labor market, and one for the odds of part-time employment versus being outside the labor market. And again, we have an effect of sex and education, and in this model, we have an intercept as well. So what you see is that for the probability of being full-time employed, there is a negative effect of sex, meaning that females have a lower probability of being full-time employed than males, which makes sense for these cohorts. For part-time employment, the effect of sex is positive, but not significant, as you can see. And then the effect of education, again, is also positive, meaning that the probability of being full-time or in fact part-time employed in the 1954 cohort is larger for individuals that have a higher education level. But actually, what is maybe most interesting for this type of model is that we can relate the labor market status to the retirement hazard. So what you see in this table are correlations between the random intercepts of being full-time employed, for the probability of being full-time employed and part-time employed, but also between that random intercept and the frailty, so the retirement hazard. And you see that, as expected, if your probability of being full-time employed is larger, your probability of being part-time employed is also larger. So you see the positive correlation coefficient. This is the mean of the posterior distribution. And you see that if your probability of being full-time or part-time employed is larger, your retirement hazard becomes smaller, as you can see in this smaller or negative correlation coefficient. And what is interesting to see is that this correlation is actually larger for the correlation between full-time employment and the retirement hazard than part-time employment, meaning that if you're full-time employed, your chance of, or your hazard of retiring is lower than if you're part-time employed. And these final 3 lines are the standard deviations of the random intersets and probability, and this basically represents the variation that we have in our population in the probability of being full-time or part-time employed or in the retirement hazard. So concluding, if we try to compare these 2 analysis methods, they're actually quite different, both in the way they typify the trajectories. So if you look at sequence analysis, you get quite detailed trajectories. You see both in the duration and the pattern that it can distinguish between groups of people. So sequence analysis is therefore also called a more holistic method, whereas the joint model is a very model-based method, and the typification of the trajectories is not that detailed. But on the other hand, we do get coefficient estimates. So if we want to test hypotheses on effects of certain covariates, then that might be a better method to use. On the inclusion of covariates, you've seen that I've included those in the joint model, but also in sequence analysis, it's possible to look at whether males or females, for example, are more likely to end up in a different cluster, for example. But it's harder there to include covariates in the models. And then a negative thing about actually both methods is in the computation. So sequence analysis requires a lot of working memory because it needs to compute differences between all pairs of sequences. So if you have a lot of individuals and a lot of time points, then this becomes very memory intensive. And then joint models, because we've implemented it in a Bayesian way, they take quite a lot of computation time. So the analysis that I've shown you are not based on the entire cohorts, but a subsample of those cohorts. And we've been trying to implement some, to try to run those in parallel, which is hard for Bayesian analyses, but we've implemented a method with which you can split your data into several smaller data sets, analyze those separately in parallel, and then combine the results after. And implemented that in an R package that's called WASPR. Yes, so thank you for your attention.
Thank you, Jolien. Very
Yes.
Interesting. I'm personally interested in your presentation, and I would like to ask if you have some results, which is the best time to pension?
Well, I just, no, I'm afraid I don't have results on that. That would mean a lot more detailed analysis. So the idea here was to sort of try to look at different methods that could be used using the pension as sort of example. Yeah. So no, I don't have an answer to that.
I can wait to see some results. And the second question is related to inclusion of the covariates. Do you intend to use more covariates in the models? I don't know, maybe the health status of the person or others?
Yeah, so actually including the health status would be very interesting and actually would lead to maybe a joint model of actually 3 variables, because you'd imagine that health status influences both when you go on pension, but also the timing of pension will probably influence your health afterwards, because working might have negative effects on your health as well. Yeah, so we're working on stuff like that as well, yes.
Okay, thank you. Thank you again, Jolien.
Yes.
And now we move forward for the last presentation of our session. Konrad Oberwiemer from the IQS Institut des Bundes für Qualitas, I don't know German, from Austria. So please present yourself. You have the floor now.
Yeah, thank you very much for the introduction. You will have the English title on the presentation. May I just ask for the thumbs up that you can hear me and see the presentation? Very well, thank you very much. So I hope before our lunchtime break, I have got something easy to stomach for everybody. I will just give you an insight on how we do things when it comes to automation in the calculation and presentation of our educational indicators. In Austria, the now EQS is responsible for the national and international assessment of student learning outcomes. International assessment is, of course, PISA, Pearls and TIMSS, and all the studies that the whole world knows now. The national assessment is the assessment of our national educational standards. That's the Bildungsstandards. And both types of assessments are defined by law in Austria. So we are a government agency that provides official statistics that also the education administration, for example, uses in its decision making. Our predecessor organizations, there were several, but mostly it was the BIFI, have done this since 2000 with the first PISA study and always providing conventional reports, follow-up analysis, and compact overviews, and so on. Also, educational indicators were provided for the national education reports that were reduced in 2009 up to 2018 every 3 years. And this was the first publication where also all statistical coefficients were provided in supplement data sheets online. But we saw a lot of limitations with this linear form of presentation, with these text-based forms that led to the development of a database of educational indicators in 2019. Mostly when you produce reports for such a long time period, there are so many PDFs and texts now on our website that it's hard to find anything. And of course, even older data we want to show again and make it possible to find it for trends. So the goals for this new database of educational indicators were provide a global and public entry point to our statistics, facilitate the exploring of contents, but also give the possibility to compare and combine results from different studies and even different data sources so that a secondary analysis are facilitated. And also very important nowadays that we have so much data and so much analysis is that citation is possible and stays the same over time. This we do by permanent designations of indicators now. There were two major restrictions in this development project. The first one was it had limited manpower and resources. We were a group of about 6 people who did this, but only corresponding to about 3 full-time equivalents. And we needed very quick results in the time period of 9 months development time, because we already promised this to the federal government that the then BIFI, now EQS, would have such a database. So I will give you a very short static tour. You can follow the link on the title of the presentation to get to this indicator database, of course. Here is a quick study static screenshot. We organized indicators in a tree-like structure. At first, you will select the general type of indicator, then a criterion. This is some state or trend of the school system that you would like to monitor or know something about. And then, of course, a year or time period for which this information is available. Optionally, the information may be split up by up to 2 variables, some regional or demographical subgroups. This depends on the concrete criterion and the data source, which are available here. And for example, this would be the highest parental education or the degree of urbanization of the schools. There is a semi-dynamical behavior. The image you see, for example, on the right side, and meta information and also links for downloading of the image and of spreadsheets are just fetched from the server after you make your decisions. So the contents exist beforehand, and no calculations are done by the web application. I will explain why this happened a bit further down the road. Along with the graph that you have seen, you get all coefficients and some supplemental information like standard errors and absolute frequencies as Excel spreadsheets with the highest possible numerical precision still preserved. So this is very good for usage in secondary analysis, that you still have the highest numerical precisions and do your own calculations on that. For example, the image you saw would translate to this Excel spreadsheet when you download it from the indicator database. So when we set up the project and we had our first project meetings, knowing the restrictions in manpower and also in time, we felt that there were two distinct groups talking to each other. It may be a bit stereotypical now, but we felt on the one side, we had the social scientists that wanted to think about the content, what to show to the public, what statistics to make available, that anticipated a lot of different indicators from different data sources. Besides the assessment data, we also have exclusive access to some official data concerning where students attend and what educations they attend. The social scientists are also concerned with the validity, of course, with quality assurance, the meaning of the indicators, and what the impact might be. So they were interested to give meta information so that users can actually interpret statistics in the right way. The social scientists feared disclosure. This is always a very difficult topic in Austria because we monitor the school system very closely, and our national assessment is not a sample, but I'm sorry, I seem to have technical difficulties. Is it the same with the audience? Can you see you? Do you still see the presentation? Okay, yes, but it may be lagging. I don't know what it is right now. I'm forced to be at home because of quarantine. Usually it works fine, but I'm sorry if it doesn't work that good. I think I will just continue. Yes, because our national assessments are not sampled. You could very easily identify single persons or single groups of persons, so privacy is of a big issue for us. The social scientists also use R, but no other programming languages. On the other hand, the programmers, of course, need to have clear goals and clear specifications. They didn't want to reprogram the web application very often. That's understandable. They can't anticipate all exceptions to the rules that we had in mind. With we, I designate the social scientists. And they rely on the social scientists for requirements to privacy to be fulfilled. That's not their area of expertise. The programmers in our software engineering department usually don't use R, but all kinds of other programming languages. So I seem to have problems switching to the next slide. So I think it worked. So we decided the whole part of producing the content, the JPEGs for the graphs and the Excel spreadsheets, as well as the meta information, should stay with the social scientists. And they are responsible for validation, for the quality assurance, and the checks for possible violations of privacy, and they do all that in R. While the programmers, of course, develop a web application, take responsibility for usability and maintenance, and publish whenever we need them to publish new indicators. And there's only a loose definition of interactions between these two groups. So I will focus on what and how are we doing the generation of the indicators in R. For every group of similar indicators, we have a separate R project because the needs to calculate something or how we visualize it are quite different. And in all of these projects, there are basically 3 steps that you could perhaps split up in 3 R files. First, there's the calculation of the estimates, validation, and concerns of privacy. The second part would produce the spreadsheets for download, and the third part would draw the graphs. After having set up several of these projects for several groups of indicators, we could abstract a project template, design some helper functions that almost any project would use, and set up some coding guidelines. On the other hand, these projects communicate very intensely with an SQL database that stores meta information on the indicators, but also tracks the progress of publishing and provides text templates or information where data sources are stored and so on. Now I will tend to all 3 parts, especially the first and the last one. The calculation for our education indicators happens with Beefy Survey. This is a package already developed with in the predecessor organization by my former colleague Alexander Robic and I. It calculates estimates and standards error for the reporting in large-scale assessments that conform to the OECD and EIA standards. This is what we are obliged to do by our scientific board. And we also want to facilitate this, of course. And we have some own definitions for the assessment of Bildungsstandards in Austria. Beefy Survey can also cope with them. Beefy Survey as a package is faster and easier to use than other packages like Survey or MI tools. The code that does the calculations runs in native C. That's much faster than R. And to make it easy to use, there is only one line of code to encapsulate the data and the data structure parameters, like weights, replicate weights, jackknife zones, plausible values, multiple imputed values, or whatever might be in there in the data. It does this by combining all these things into an object of class Beefy data, and all the following functions for estimating and calculating just use this object. For example, you see such a function called to the function beefy.data at the bottom of the slide. Here I would set as an input the 10 imputed data sets from the baseline study of the Bildungsstandards. That's just a list. I would define a weight, which stood, and I would provide several vectors for 132 replicate weights from the jackknife procedure. Afterwards, there are easy to use functions for typical reporting needs, frequencies, univariate statistics, correlations, and so on. In the example, you see frequencies by the means of the function beefy.frequency. We pass on the beefy object and then just select which variables we want to have frequencies for, and also a list of grouping variables so that we get split results. Beefy Survey can also handle more complex models, but this is not usually the case for our official statistics. Moreover, Beefy Survey has a standardized output format for results. Estimates and standard errors are always provided in a long table format, and this makes it possible to write very easy helper functions concerning privacy. We check all our statistics for K anonymity. We don't want to provide any estimate for a group of size below 5, because again, it's not in the national assessment, it's not the sample. You might perhaps know the 4 people of a distinct demographic group, and we don't want to share the information for such small groups. And we also check for zero variants and also categories that have 100% for any given group, so that you can't distinguish from come from one result to result of people of the group that are all similar. What I didn't mention is all of these functions that we use here are very suitable for interaction with an SQL database, where you just fetch which variables you want to get results for, and what are the grouping variables. So in a big loop, we can very easily calculate results for a huge number of indicators. I won't lose many words on producing the spreadsheets which open XLSX. I will just point my opinion, this is now the best package for creating XLSX right now, at least for the needs that we have. The last part was the trickiest. It was to produce graphs that not only are informative and are hopefully good looking, but also are conform to our corporate design. This is now that we are actually an agency of the Federal Ministry for Education itself. This is more than before now an issue that you have to apply to the corporate design. So many of the packages that are available to produce graphs directly from R, like ggplot, were not really feasible for us because we needed so much code and so much definition to get everything right, the colors, the thickness of lines, and so on. So we devised our own tool that's called SVG tools, and it works that way. Our designers produce templates in Adobe Illustrator, like the one on the right side, that are uninformative. All the values here are just somewhere on the scale and not where they actually should be in the end. They don't know about the correct values and don't need to know about them. They just put all the graphical elements there and they name them. SVG is just an XML format. So when you convert it from Adobe Illustrator to SVG, all the elements that had names in Adobe Illustrator now have an ID tag in the XML representation. Like you see on the left side, there's one rectangle that is called Rahmen or frame. And there is one group of circles that would have the ID K1 M8. SVG tools then sets the graphical elements right. It rescales and repositions them by using these designations that were given for them. You see in red the frame where we need to position the elements is called Rahmen, and the group is K1 M8, and we pass on the calculated values. This is what we social scientists again estimated, and so in the end we produce the graph that you see on the right with the correct values here for differences in mean achievement for sex and split by degree of urbanization and status of immigration. The overall perspective to this way that we did it in 9 months is that given our limited resources and development time, I think we have used fine combinations of tools and procedures in R to generate a predefined set of education indicators. Yeah, you see what we can't do right now is something like Statistics Austria has with StatCube, that the user can calculate whatever he or she may be interested in themselves. The reproduction of all current about 1,000 indicators takes about 2 hours on a standard PC, not counting manual validation steps, of course. So when we want to get rid of a spelling error, or that hadn't happened luckily, but some miscalculation, for example, it's not a huge effort to produce all the material once again. And from my experience, generating a new set of indicators from the definition, calculation, designing the graphs and so on, takes about a week for one scientist. So this is also very satisfactory. And when next year the new National Education Report will be published, we will have much more indicators also in the database. The biggest limitation right now is to predefine what we want and also expect what the public and administrative demands for knowledge would be. Because that we have to do ourselves. Nobody can get access that way to the microdata. We have other facilities for these needs. And we still need social scientists with at least better skills in R that are not fearing programming structures like if, else, and loops, and who can also manage database access to use everything very conveniently. So I thank you for listening to my talk, and I'm looking forward to your questions.
Thank you, Konrad. Very interesting presentation. We have for you a question coming from Olaf. He appreciated a lot your presentation also.
Thanks.
And he said, very interesting view on social sciences versus programmers. Do you see in future a more narrow gap between them, or will this stay, and do we have to accept it?
No, in our institution, the procedures for creating software and interacting with the scientists are currently revised, and it's turning to agile software engineering with tools like Scrum, where the software engineers and the scientists collaborate much more intense.
Okay, thank you. Another question coming from Alex Kovarik. Is the way graphical designer defines CAVG and expert fill it with values a wider strategy for visualization in your institute?
I'm sorry, I didn't get it. I'm reading it right now.
Okay, maybe it's better.
Yeah, yes, sorry. No, I get it. Yes, it definitely is. We took SVG tools on CAN just 1 week ago. So this is version 1.0, but we want to elaborate on that. The next issue will be that, of course, the designer doesn't have to put all the graphical elements in the design beforehand, but that the software intelligently duplicates elements and has a better understanding of where they should be put in the graph.
Okay, thank you. If there are not any more questions, our session will be closed. Please, Alexander, if you have something to say before the lunch break, you have the floor now.
Just thank you to all the presenters of this session, and thank you to Matthias for the morning keynote. We will start again at 2 with the next session, so at least half an hour before there will be the WebEx open. If you want to follow via YouTube or Facebook stream, then the links will be posted on our homepage also during the lunch break. So have a nice lunch if it's at the time for lunch where you're located. See you later. Bye-bye.
Thank you. Bye-bye.
Bye.
Thank you. Bye-bye, Alex.